Hello students, today we are going to start a new chapter. This is chapter number 7 and this is a frequency response. This is all about. So frequency response, yeah. So we will be actually analyzing, or you can say analysis and design of control system, using frequency response method. Okay, so this is all about how system behaves when you have an sinusoidal input. Yeah, the output will be sinusoidal only. So this is similar to what we studied during the vibration section. So let us say you have a spring mass damper system, yeah, and then applying a force Ft, and then you have a displacement xt, and you found out that equation will be mx double dot plus cx dot plus k equal to ft, and then you take the Laplace transform, then you get ms square plus cs plus k, assuming x dot 0 equal to 0, x 0 is also 0. Yeah, so from where you are starting. So then in that case it will be like this one, ms square plus cs plus k, xs equal to fs, and hence the transfer function that we now have to relate to is equal to xs over fs, and which is equal to 1 over ms square plus cs plus k. Yeah, and then if you want to find out the how this behaves, let us say if ft is equal to, let us say, f naught e to the power I omega t, then we assume that the xt will be of the form of x naught e I omega t plus phi, and you put it here, right, in this equation, both of them, and what did you find? You found, if you put it that, you found m minus m omega square plus I omega c plus k, right, and then you got x naught e I omega t plus phi is equal to f naught and e I omega t, right? And then from here we will get what? If you take the if you want to find out x naught over f naught, this is a repeat of what you did during the vibration class. I'm just repeating here so that it makes sense to you. So x naught over f naught, if you do, then what do you get? From here you get is equal to 1 over, so x naught here, f naught here, so you will get 1 over minus m omega square plus I omega, yeah, plus k, right, and also you will have here multiplied by e I phi. Here remember that here like I square omega square is there, that's why it is like this. So let us write like this one, m I omega, this is how it was actually. If you put it there, how it becomes I omega will be here, right? Double differential here. So plus this is C, and then you have C times I omega and plus K, and here you have e to the power minus I phi, right? So this is what you have. You get like this one. Now the x naught over f naught is simply, this will be equal to 1 if you take the magnitude of that. The amplitude will be 1, and hence what you get simply x naught over f naught will be simply like this, equal to 1 over here m I omega square plus c I omega plus k, right? Simply it will be this is what you get. This is the magnitude, the ratio of the magnitude, ratios of the output amplitude divided by the input amplitude is equal to simply like this one. Now you can relate with the transfer function, right? This is simply, this is nothing but, we can write a double also. This is a complex number, so we can write double like this, yeah. So this is what the magnitude will be, the amplitude, right? So this is, we can write it as, this is Ts, so we can simply write, if you compare here, S here, I omega here, S here, I omega here, like that, simply as if you have just a transfer function here, and you have put, instead of S, you have I omega, simply. You will get the ratio of the amplitudes of the output and input, right? So x naught over f naught equal to simply the transfer function with I equal to I omega. You take the magnitude of that, you will get this thing. Yeah, as simple as that. Okay. Similarly, we can also find out the phi. Okay, so let's drill this one, and we have this equation. Okay, so we have to find out the phi now. So how do you do? From here, from this equation, how do we get? We get I phi is equal to, simply is equal to, this will be f naught over x naught and divided by minus m divided by this only, right? So minus m omega square, basically this one, simply, yeah. So this will be simply this, so just write like this, is equal to m I omega square plus c I omega plus k, right? Okay, that really means that if we take the angle here, right? So if you say angle like angle EI phi is equal to angle of this, right? So f naught over x naught and 1 over m I omega square plus c I omega plus k, right? And then what we get from angle of this is phi is equal to this. This is a constant. Constant has no meaning here because the angle depends on the ratio of the imaginary part to the real part. Hence, that if you multiply it by some constant, there is no meaning there. So f naught x naught are constant basically. Yeah. So that really means. So here, in fact, we can also write actually the x naught and f naught basically in this case are they are basically magnitude. Remember this, all the magnitude, yeah. So although we are writing like this one, actually the meaning is x naught over f naught has to be the magnitude of that, so it has to be the magnitude, yeah. So but we this will have the angle and the magnitude both. Yeah, so here the real meaning of that is the magnitude, the ratio of the magnitude will be like this one, and the phi will be given by this angle. And what is this angle? This will be angle simply angle of 1 minus, right, minus angle of, here you have 1, right, so 1, so basically what we get, 1, and then you have m I omega square plus c I omega plus k, and if you look at when you have 1, meaning that you have basically the angle of what? 1 plus I0. So sine is here, cos is here, and hence this means sine phi is equal to, or some angle, let's say theta, sine theta equal to sine will be equal to, or say tan theta. This one is cos, this is sine, and what you get? You get sine theta equal to 0 over 1 equal to 0, so theta equal to 0 simply, right? So that it tells you that this is 0 minus angle of this, whatever angle this is making, right? Or simply you get equal to, phi will be simply equal to, phi equal to minus angle made by m I omega square plus c I omega plus k, right? So this is you get the phase angle. Yeah, so you get phase angle. Okay. So we started with AF naught and X naught as the magnitude basically, yeah, and then when we divide we get this ratio, meaning that here what we get is the ratio which has a phase difference, and hence we are getting a complex number, yeah, and this also depends on the depends on omega as well, yeah, and hence if you want to the magnitude, real magnitude of that, we have to take the real magnitude of that. If you want to know the phase difference between the two, then you have to take accordingly the angle, and you will get that angle. What you get simply in this case, what you see is from the transfer function you can get it. So that really means the same thing. Now on, we don't have to repeat. What we have to know simply is what is the transfer function, and for example, in this case we can simply write here the phi will be equal to, so let's remove this one. So phi will be simply phi equal to simply angle of transfer function I omega. Simply we can just write like this one. Yeah. So this is what you get, phi equal to angle of transfer function. That's it. Which will give you simply phi equal to this. It is the same thing. So if you want the magnitude, so we can write here so x naught f over f naught is simply the magnitude of the transfer function with s equal to I omega, and phase angle is nothing but angle t I phi. That's it. Yeah. So we took long but very simple solution it has, and we can apply to any kind of transfer function. We can extend that to the general purpose transfer function as well. We can write, for example, I'm putting input is still, I'm keeping it as say y, yeah, okay, and output is x, yeah, okay, so that we are not confused. Output in other case, earlier it was f, so okay, we can also have f, no problem, let's put like f also, there's no problem, like this one. Okay, now the input is force and output is x. Now I'm writing the general terms, so we can write something like this, a, right, a n x to power a n d n x dt n plus a n minus 1 d n minus 1 x dt n minus 1, and so on till a0, let us say. And then is equal to, we have the other side bm, and then dmf. You can, that side we can write as f, like this one. Yeah, f, right? Okay, and then we will have right, and then we will have d tm, then bm minus 1 d m minus 1 f dtm minus 1, so on. Then we have b1 f, and then b naught. Let us say it is like this. Note that, however, that this constant a naught, b naught should not be there, otherwise we cannot get a transfer function. You know, transfer function as a ratio of polynomials. If we want to get, a naught should not be there, b naught should not be there. We will see why I'm saying that. So basically here at the end we will have a1, yeah, a1 x here. Similar to, you have mx double dot plus cx dot plus kx, and after that there is no constant there, right? So hence here there is no constant. Similarly at the other side you have f only. You don't have like f and then plus something else. Yeah, so that really means that then only if you take the Laplace transform, then you can get the ratio. If you have a constant, we cannot get the ratio. Yeah, so that's why. Okay, now this we take the Laplace transform on both the sides. Yeah, and what do we get? We get an, and then x s is, so we write like this now, an, then sn plus an minus 1 sn minus 1, and so on, and then a1, and then we have xs, yeah, is equal to, similarly here fs common, and then you have bm fs, sorry, bms to the power m plus bm minus 1 s to power m minus 1, and so on to b1, simply b1. Yeah, and hence the ratio transfer function Ts equal to xs over fs. Yeah, and will be equal to bm sm plus bm minus 1 sm plus 1, and so on till b1, and then divided by, you have an sn plus an minus 1 s minus s, not plus 1 here, sorry, it should be minus 1, and then here also in minus 1, and then we have a 1 like this. So we have the transfer function like this one. Yeah, and same kind of analysis we can do, and we will find that the simply if xt, what is the input? If f equal to f naught e to the power I omega t, then solution of this differential equation will be x equal to x naught e I omega t plus phi. Yeah, and then you put this value to differential equation, and you can do follow the same method that we did for the spring mass damper system, and you can find that in this case also x naught over f naught will be equal to simply the transfer function t I omega, yeah, x naught over f naught will be t I omega simply, and the magnitude of x naught over f naught will be equal to simply magnitude of t I omega, and what we get, angle phi, right? So angle phi, where the phi is the phase shift, yeah, okay, will be equal to simply angle of t I omega, yeah. So you will get the same thing what we get earlier. So this is the general solution, general differential equation. Based on that we get the different kind of differential equation, and the earlier was just one example to demonstrate that is true, and you can also relate physically what is the meaning of that actually. Okay, so of course that really means that if ft is f naught sine omega t, then xt will be simply x naught sine omega t plus phi, whatever phi you get will be added. Okay, so this will be the, if input is this, output will be this one. That's what it tells you. If the transfer function is given, and then if input for the same system like this is system will be like this. This is the system transfer function. This is input. What is the input? Ft, and output is xt. Okay, so if this is the system, then if the input is f naught sine omega t, the output will be x naught sine. So if input is this, then output will be x naught sine omega t plus phi, where this is given by phi is given by this, and x naught is given by this. Yeah, so x naught is given by what? X naught will be x naught. The magnitude is so you can write here, where x naught equal to this one, x naught equal to f naught, yeah, and then we write like this also, t I omega simply. Yeah, here x naught and f naught are sort of complex number formulation, but like it's a general solution. But when we spell out this is the real numbers, then finally we know that f naught is a real number. So x naught equal to f naught times t, the magnitude of t I omega, and that will give you the x naught. So this is how the system will behave under the sinusoidal input. So you already know what is the meaning. We have understood in terms of the spring mass damper system. So you can assume any transfer function as if this is the transfer function of a spring mass damper system, and accordingly you can visualize what is the meaning of that, what is the meaning of like harmonic input. Yeah. So whatever we learned can be used for drawing or making the what is called Bode diagram or Bode plots. Okay, and it is simply as we looked at already, this if the transfer function, okay, if the transfer function Ts, let us say, is equal to the output, which is xs over input, let us say fs, is equal to So Ts is equal to this one. Okay, so just like this one. So this Bode diagram is nothing but the log plot. Yeah, so this is a log plot of what? Plot of first the magnitude T I omega, okay, versus omega, but log. Okay, so details we will find out. Log plot of this, and second will be the phi, yeah, or simply the angle T I omega versus omega. So this is what known as Bode diagram, and if we know this Bode diagram, from there you can find out a few things about the system, yeah, even stability, for example, yeah, all those things we can find out. So that's why it's important. We will see what is the use, but right now we concentrate on the plotting it, yeah. Okay, so now this log is true, but what you have this one in decibel, yeah, so decibel, okay? And that really means is 20 log, yeah, on base 10 basically, yeah, of this, of T I omega, okay, versus this one is nothing but 20 log T I omega versus you have log omega, yeah, all base 10, remember. Okay, now the this one, this angle here, this angle will not be in log plot, remember. So only this is in log plot, not this one. So basically we can log plot of this one, yeah, but not of this. This one is simply this versus log this one, remember. So okay, so log of this versus log of this, and simply whatever it is versus log of this. So we have from one you have that, from the second one you have angle T I omega versus log 10 omega. So this is what it is basically, yeah. So next thing is drawing actually. So let us say we can understand by some example only. So let us say first order system, right? First order system. Take one example. Example will be something like Ts is equal to 1 over S plus 1, for example. Yeah? So this is first order system, and then we from here the system will be like this. So this is the Ts, input is Ft, output is Xt, or input is Fs, output is Xs. Okay, so this system will be could be something like this: a spring and damper. That's it, nothing else. And the value of k equal to 1 and c equal to 1, and then you have simply x dot plus x equal to f, and hence you get this transfer function. Yeah, so this is one example. Yeah, so this is what this system is. This system is like this. Okay, now then we have to find out if we give a sinusoidal input, right, then what will be there. So we know that the magnitude ratio, or T I omega, will be simply is equal to 1 over I omega plus 1 magnitude, and what we get is simply 1 over omega square plus 1 square root of that. Yeah, that's what we get. And angle phi, we will get angle T, right? So we just write phi is equal to the angle T I omega, and which is equal to angle 1 over I omega plus 1, which is equal to 0 minus I omega plus 1, yeah, and which is equal to minus tan, right? Minus tan inverse what? So this is cos, this is sine, right? This is cos, this is sine. So we have tan inverse omega only. Yeah. Okay. So tan divided by tan phi is equal to tan. Here this is the tan theta, this is the cos theta, and hence you get tan inverse omega, let's say. Yeah. So phi will be simply minus tan inverse omega. So we get 2 of them. Now next thing is just plot, basically. So we get this we have to plot 20 log of this. So we have to take 20 multiplied by half log of 1 plus omega square plus 1 versus log omega, and here we have this one versus log omega, right? That's what we need to plot. So let's plot this first. We have to plot the magnitude, or simply this one. So how we are going to plot? This will be T I omega, magnitude of that, which will be equal to simply 10 and log 1 minus log omega square plus 1, right? Which is equal to 10 log 1 is 0 minus log 1 plus omega square, or simply equal to minus 10 log 1 plus omega square. Yeah. Okay. And then you have phi is equal to minus tan inverse omega. Yeah. And we know that when omega equal to 0, then we have phi equal to simply 0, omega equal to say 45 degree, we can put the like this one. That really means omega equal to minus tan phi, that really means, okay. And that really means when phi is equal to 0, omega will be 0, phi equal to minus 45 degree. That means omega equal to, so minus 45 degree is 1, so that omega equal to 1. Yeah. Okay. And then if phi tends to infinity, phi equal to 90 degree, minus 90 degree, okay, and then omega tends to infinity. Yeah. So this gives us some idea. Now plotting this, how we have to plot? So we have like this. Yeah, so this is log omega, and here we are going to plot this T I omega. Yeah. Okay, and this will we can make little bit approximation here when we are going to plot it. So what approximation? So let us say when omega is this one, when omega is very, very less than say 1 in this case. Yeah. So in that case, what happens? That time this Ti omega will be equal to simply minus 10 log 1, which is equal to 0. And when omega is very, very larger than 1, then what we get? We get Ti omega is equal to, since this is bigger than 1, much bigger than 1, we can simply have minus 10 log 1 plus omega square equal to minus 10 log omega square equal to minus 20 log omega. Versus what? Versus log omega. So what we see here, there will be a slope. It will be as if it is going to be a linear, right? With it is changing with omega, log omega. This is directly proportional. That becomes directly proportional to that. Yeah, that's how it becomes. So how can you plot? You can plot. It is going to be 0. So let us say this is 0 point. So this is 0. Yeah. So but we have to write here 20 log this. Yeah, 20 log of this. It will be 0 till it's 1. You can say before 1, this will follow something like this. Yeah, and after that, this will become a straight line. That's what it tells you, right? It is going to be a straight line with some slope of minus 20, right? So after that, this goes something like this one. So this will how it will look like. It is not a straight line. Actual curve will be something like this. Yeah, but we can approximate it as this one. Here, this one is log omega equal to 0, so you can have a 0 here. Yeah, so log omega equal to 0, and from here it is a straight line. This is log omega. That only means omega equal to 1, right? And from here it is going down like this. Yeah, you can have here slope equal to minus 20 here, right? Because see the relationship here. Similarly, we can draw the phase here, but remember that in Bode plots you have typically both the plots together, meaning the upper portion will be the magnitude plot and the lower portion will be the angle plot. Yeah, so although I am plotting it here, but remember it should be plotted together. So like a same thing, same scale basically. You have the same scale which is for log omega, and then you plot here like this one, and here you are going to plot the angle whatever we are plotting here. So what will be the angle look like? So again we will have axis for this log omega, okay, and then we know that when omega is equal to 1, so same as here, right? This is omega equal to 1 or 0, right? That is omega equal to 1, log omega equal to 0. If you have there, then you have minus 45 degree. So let us say minus 45 degrees here. So just write minus 45 degree. Then phi equal to minus 90 degree at omega equal to infinity. That means log omega is infinity. And then phi equal to 0 as omega equal to 0. Yeah, so that means phi equal to 0 will be omega equal to 0 will be somewhere here. When you say omega equal to 0, log omega will be minus infinity, right? Omega equal to 0 will be, log omega will be minus infinity. So in the minus infinity, it is going to be 0. So at some point, let us say where omega is very, very small, we can start, let us say if this is 0 degree, so this could be, let us say 0.1 or so, yeah, 0.1 minus some minus value, let us say minus 0.1, let us say, let's call it like this. Yeah, so here this will be not exactly 0 here, because the phi equal to 0 when omega equal to 0, but when omega, in this case omega is log omega, so basically what we are saying is 10 to the power minus 0.1. Yeah, so maybe let's call it -1 only. Okay, -1, so that we have 10 to the power -1, something like this. Yeah, when omega equal to 10 to the power -1, let us say. Okay, so this point here, the phi will be very close to 0, but not exactly 0. So let's say start from here, and from here this is going to be go here and then go like this. Yeah, so it will go like this. So what we will see is this is a asymptote basically, and finally this will be 0 in the infinity, minus infinity somewhere. Yeah. So this is what the phase will look like. So here this is not 0, minus 0 is phi equal to 0 is okay. This is 0, of course. This is minus 90. So this is 0 degree, this is minus 45 degree, this is phi you are plotting, and this is the minus 90 degree. This is how it goes. Yeah, so what we see, if you have this one below this, so then this will look like, so this is log 0 equal to 0, and hence you get something like this. So you can plot like this one. Yeah, same thing will be there. So this is what is known as Bode diagram. Okay, so this is known as Bode diagram. Now let's look at the second order system. Okay, so in second order system, the transfer function we know that is given by Ts equal to omega n square and then ms square plus cs. It could be, okay, let's write like this one. Originally we had this equal to s square plus 2 zeta omega n plus omega n square. Yeah, okay, and this we can write it as equal to okay, so like this. Now we know that ti omega will be equal to omega n square divided by, and then you have here minus omega square plus 2 zeta omega n, right? And then oh, this is I here, 2 zeta I omega n plus omega n square. This we can write it as, so we bring it down, so we get minus omega square over omega n square plus then I, then 2 zeta omega over omega n plus 1, right? Or will be equal to 1 over 1 minus omega square over omega n square plus I, right? And then you have 2 zeta omega over omega n. This is what you have simply. Yeah. Okay. Now, if you have to plot the magnitude, so we get T I omega, okay, will be equal to this, or simply we are going to plot the decibel unit, so minus 20. So minus 20 log of T I omega will be given by minus 20, then log, yeah, and then this T I omega, so we'll have 1 over, then we have this will be simply 1 minus omega over omega n square plus 2 zeta omega over omega n square, right? Okay, like this, and this will be a square root of that. So 1 over 1 minus omega square n square plus 2 zeta omega over omega n square and whole square, like this one. Yeah, or simply we get equal to the minus, sorry, not minus, it will be 20, let's log. So we get 10 log, and then will be 1 because of this, so becomes minus now, and then we have this 1 minus omega square omega n square plus 2 zeta omega over omega n square, right? So this we have to plot, right, versus what, log omega. So we can now identify based on the range of the value. So one will be, the first will be omega is far less than omega n, right? So in that case, what happens? That really means we do like this. First we want to neglect. So first what we want, we can write like this also. 1 is far bigger than omega over omega n, and that is when omega is far less than omega n. Yeah. And in that case, what happens? If omega over omega n very small, in that case we can neglect this one, we can neglect this also, and in that case the minus 20 log T I omega becomes equal to 0, right? Now this is the case number 1. Case 2, the case number 2 will be opposite. When 1 is far less than omega over omega n, means omega is far bigger than omega n, and in that case, or simply you have omega n omega, just opposite of that case. Okay, in that case, what happens? In that case, this we are going to neglect because this is much bigger, and here if you see here a square and then a square again, but here just one square, so that means only this will dominate. So we will get minus 20 log T I omega is equal to minus 10 log, and then you have just this, meaning what? You have just this omega square over omega n square is square. All other can be neglected because they are small. Yeah? They are small in comparison with, I mean, this can be neglected, and this can also be neglected because this is the bigger power. Yeah, so because of that, and hence you have 4. So minus 40 log omega over omega n. Yeah. Okay. So what it tells you is here this is sort of a line basically, yeah. As in the previous case we got minus 20 log omega, here we are getting minus 40 log omega over omega n. Number 3, when 1 is equal to omega over omega n, and that really means omega n equal to omega, and in that case what happens, this will cancel out, and what you have is just this one, yeah. And in that case you will have minus 20 log ti omega, right, equal to, you get simply, you have minus, in that case this will be gone, only you have this one, and hence it will be minus 20 log, minus 20 log, and then you have 2 zeta omega over omega n, yeah. Okay, so minus 20 log 2 zeta omega over omega n, that's what you get, yeah. Okay. One thing we missed, that here omega over omega n, omega equal to omega 1 basically, yeah. So in that case this will not be there, right? So we have just 2 zeta, yeah. So we have 2 zeta simply, so you have 2 zeta, that's it. Now let us plot it. So how will it look like? So we are going to plot this one, and we start like this, okay. So this is going log omega, we can write in terms of log omega over omega n also, yeah. So but let's say log omega, and then we have we know that when omega is very less than, omega is very much less than omega, right? So let us say here, yeah. So when omega equal to omega n, okay, not that. So here, this point, let's refer to this, omega is very less than omega n. At this point, the value is 0. So we have 0 here, yeah. So let's have 0 here. But what are we plotting? We are plotting minus 20 log of t I omega, yeah. Okay, and then, and okay, so here, then we somewhere we have omega equal to omega n, and then that really means the log omega over omega n equal to 0, yeah. So so at this point what we get, we don't know, we get this actually, yeah. So let's have this like this, okay, okay. And then from here we second case, when we have omega far greater than omega n, then it becomes a straight line, right? So this this goes something like this after that, yeah? Where slope is equal to minus 40, yeah. Okay, I think in order to visualize nicely, we can also have omega over omega n basically. That way that makes it equal to 1, log 1 equal to 0, so that we get omega over omega n equal to 1 in this case. And then you can see that when omega over omega n equal to 1, this log 1 equal to 0, and hence you have 0 here, yeah. And since from there you have like a straight line, right? So at log omega over omega n equal to 0, value is 0, and then it is proportional, yeah. So minus 40 is the slope. From there you can see that. Okay, so from here it goes like this, and before that it goes like 0, right, till you can say it is something like that. It is going when what it gives you is like asymptote basically, right? This one is because this is going to meet in the infinity. However, remember we have, depending on zeta, we have different at omega equal to omega 1 here. At omega equal to omega 1, this is asymptote, that meaning that the actual curve where it is meeting, because we have assumed omega is far greater than omega n. These are not the actual curve, but this is the asymptote that tells you. Yeah, this also is asymptote because this is telling you that when omega is very less than omega n, then what happens? Or simply when omega over omega n is far less than 1, then what happens? That is, it tells you. In between, when you have omega equal to omega n, it simply equals to minus 20 log to zeta. Let us say if our value is 1, for example, yeah, so then you will have a different value, yeah, so and so on. We can see that from there. So for example, if zeta equal to 0, what you see is minus 20 log 0, and log 0 is minus infinity, so you have infinity there, right? And in that case, this will be a, so it will go up, very much up, and from here, this is going to go down. This is for what? This will be for zeta equal to 0, but close to 0. It will be very up. Yeah. So resonance, what do you call it? Resonance. Then when zeta equal to say 0.5, and then what you get? 2 times 0.5 is 1, so log 0. So this is like this only. So zeta equal to 0.5 will be something like very close to that. It will go like this. Yeah, something like this one. So this is what you have, zeta equal to 0.5. Now in between you will have in between. So let us say zeta equal to 0.4, for example. Then this may go like this. So this is zeta equal to 0.4. Yeah, and so on. If zeta equal to 0. This could be here. This one could be for zeta equal to 0.3, and so on. If you plot more from 0.5 is exactly here 0, it could you can plot more. Let us say this. Yeah, so this could be zeta equal to 0.7, and even less here. It goes maybe something like this. Right, so this could be zeta equal to 1, and so on. So what you see here, the figure will be something like this. If you zoom, if you take into account all of them. So what we found here, so this will be like this. So on. This is how it will look like basically. And here, if you want to visualize how it will look like. So this will be around zeta equal to omega equal to omega n, around that. Yeah, and that we have seen in the while studying the vibration. However, we did not take the log of that. We did not express that in terms of the decibel. Here we are doing the decibel. Log plot, there we had simply simple plot basically. That is what the difference is, but you know what it is. Similarly, we can plot the angle, or let's call the phi is equal to this t I omega, and we know that angle of what? 1 over this is omega n, so this s square here, so this is I omega plus 2 zeta I omega plus this is omega n square plus omega n square here, right? So this is how it is, angle of this one, and hence this is equal to angle of 1 over, and this we get same as earlier, like we get here 1 minus omega square over omega n square plus I 2 zeta omega over omega n, right? So that's what we had got. Yeah. So okay, and then the angle will be phi will be equal to angle of 1 minus angle of 1 minus omega square over omega n square plus 2 I 2 zeta omega over omega n, yeah, is equal to 0 minus angle of this, angle of 1 minus omega square over omega n square plus I 2 zeta omega over omega n, yeah, is equal to minus, and this will be simply the tan inverse of tan inverse. This you know that this is cos, this is sine, so you get 2 zeta omega over omega n divided by 1 minus omega square over omega n square, right, of a square like this. So this is what the angle is that we know. Now only thing is plot them, and plotting we can, this has to be versus log omega we have to do, and we can plot accordingly, and we know that the values when omega over not this one, we can, this is not relevant now, so we have from here we get phi when omega is much less than omega n, right? When omega is much less than omega n, means 1 is very greater than this one, yeah, and in that case you will have phi equal to minus tan inverse, and this will be 0 basically, very small, omega is telling very small, so it will be almost 0, and this will be 1 basically, so this will be 0 only. Now when you have very large, yeah, and then in that case what do you have? You have this value will be very large, so this is not there, yeah, so you get minus equal to minus tan inverse, and then you get 2 zeta omega over omega n divided by minus omega square omega n square. So what you get? 2 zeta divided by minus, so you get a square of that, so okay guys, there is one problem, here it should not be a square, you know, so this is omega minus omega n square, that's it, okay, not a square, yeah, it will not appear, yeah, this is not correct, should be like this, yeah, okay, so otherwise it's correct. So you have 2 zeta, and then omega over omega, and this will be gone, so you have minus omega over omega n, right? So this is what it will be, okay, and then when you have 1 over omega n, 1 equal to omega over omega n, means when omega equal to omega n, this will be infinity, yeah, this is going to be infinity, the ratio, and hence you will have phi equal to minus tan, and this is going to equal to 0, yeah, okay, so this will be tan inverse, Okay, remember here we have minus tan actually, so we have minus tan, so minus tan inverse, and then we have infinity, right? So infinity, which is equal to minus 90 degree, right? So 0 degree, here we have minus 90 degree. Okay, in this case you see like 0, 90 degree, and 180 degree or minus 180 degree, this is the same one only. So this gives you the minus omega over omega n, where omega over omega n is very large than omega over omega n is very large than 1. Okay, so this is large value basically, and that really means the whole thing becomes 0. So tan inverse 0, this is actually 180 degree, you get minus 180 degree or plus 180 degree. So how exactly that we can analyze more. We can see in the vicinity of that, when omega goes to, as omega approaches we can see this way. This is the value, this is omega over omega n. When this is very large value, this is a negative number, right? So this is a negative number. So when we tan inverse of negative number but 0, we can think that way. This is approaching 0 but approaching from the negative side, because of a negative sign, and hence you have 180 degree here. You have 180 degree and but minus sign, so like this one. So simply what it tells you, that we can draw the phase diagram, and this will be log omega, and what it says, log omega over omega n rather, and when omega over omega n is far less than 1, in that case you have 0. Let us say this is 0, and then you have omega equal to omega, this is 1, 0 basically, meaning that log omega over omega n equal to, meaning that omega over omega n equal to 1, equal to omega n. Yeah, so in this case this is going to be 90, so here let us say it's a minus 90 here, and this you can call this is minus 180 degree, and this is where the transition is. So this will be something like this. It goes here, and then goes towards 180 degree. Yeah. So this is how the angle below, the phase angle, this is what the phi you are plotting. From 0 it is going to 180 degree, as omega goes from very small to very large value. So this is what we get for second order system. Okay, that is all for today.